No, wait just a minute.
It should be
2.66. All right, so she says it should be 2.66. So each one of these manganese has a charge of plus 2.66 on it. John, look at your periodic table there. Look under manganese and tell me the black numbers for manganese. Because remember, this is something you did not have to memorize, right? And I see he's got a nifty periodic table there.
Got 2.
Plus 2.
3.
Plus 3.
4.
Plus 4.
6.
Plus 6.
7.
All right, and 7. So you see how lucrative manganese is. Using these numbers, how can we make it happen? Because this whole thing has to be 8, right? Well, could we have this one with a plus 3 and this one with a plus 2? Is that going to do it? So is that a little bit better for you than a plus 2.66? So let's name it. This would be a manganese. What? What charge is there? 2, comma, 3 oxide. This compound is what is called mixed valent. In other words, it's got manganese having its plus 2, which is common for manganese, right? That's not one of the ones you had to memorize. And a plus 3, which is common for manganese, all in one compound. And it turns out that these type of compounds sometimes exhibit neat chemistry behavior, right, as many as you can imagine, because it can react one way and another way, right?
Why did you write it only 2 and 3 manganese?
2, 3, because it's got both a 2 and a 3 charge for manganese. Yeah, I know. We just don't put that. Right. Mm-mm. Now, of course, you would not be expected to name that, right? But, just to show you, if Cassandra started making some of this right here, I would turn my ears on, right? Because it's like, wait a minute, she got something here now. She's got a compound that's got a couple of oxidation states in the same compound. That's a mixed valent system. That's good, all right? Because that means electrons can start jumping around in a variety of different ways, not just one. How we doing? Good? All right. Now, what is the difference in an empirical formula and a molecular formula? Does anybody want to venture at that? Well, everything we've been doing here is empirical. Empirical means it has been experimentally determined. On Thursday, you're going to stand on your feet, you're going to run the experiment, you're going to figure out what the formula of magnesium oxide is, all right, using a balance and a periodic table. Well, that's your empirical formula. An empirical formula is always reduced, right? Think of the examples we've did today. We did CuCl2, we did Mn3O4. What else have we done? KPO4, K3PO4. Is that it? Okay, what's the common theme? These are all reduced. These are all empirical formulas. Take a look at this joker, N2O5. Oh, let's do N2O4. Is that an empirical formula? No, that's a molecular formula. What is this one's empirical formula? NO2. So if you were trying to have data that you could find this thing right here, its empirical formula would be NO2. Why? Because no matter what compound you build, it'll always have to have that ratio if it's coming from this compound. All right? An empirical formula is always the one that's reduced. Remember what the term molecular means, and the term molecule means that it has a covalent bond. So look at here. Is there a covalent bond here? What do you think? No. There's a metal. Is there a covalent bond here? No. All right. There's a metal present. So here, is there a covalent bond? Yeah, well, it's got a molecular formula. Okay, let's look at this one. C6H12O6. What is this one, empirical or molecular? Molecular. It tells the chemist how glucose is connected. What's its in? Okay, so this is an MF, molecular formula. What does the empirical formula? What does the empirical formula tell us? No, wait just a minute. CH2. Oh, right. 6 divided by 6 is 1. 6 by 6 1. And 12 divided by 6 is 2. So this right here is the empirical formula. All right. So you see the difference in a molecular formula and an empirical formula. Now some things out there, let's switch gears. This right here, okay, it's called formaldehyde. That's the stuff that they use to embalm like cats and whatnot. All right. What is this formula? CH2O. This right here is a molecular formula, and it's also an empirical formula. So some things out there have both an empirical and molecular formula that are the same. Now, do you see how this would have a molecular formula? This has covalent bonding only. There's only nonmetals here. This right here, there's metals present. This can't have a molecular formula. All right? Is there anybody that's confused about this? Okay, so how do you get molecular formulas? Well, you have to use something called a mass spectrometer. Okay, and what a mass spectrometer does is this is a very simple one. There's a source here, okay, that you can ionize a chemical with. And then there's this huge magnetic field. Okay? So, here comes an ion that flies through that magnetic field. And over here's the detector. Okay? Now, what do you think changes the trajectory of how that ion flows through there? The what? The magnetic force, but it's constant, right, throughout. So what else would change if something traveled a huge, big, slow radius, or something traveled quickly? Weight. Charge is right. Who said charge? Right. Both of them are correct. This is called a mass selector, right? Because what the answer I was looking for was what John said. There's a huge big radius. This right here is going to be slow, which means it's going to weigh what? A lot. Okay? And then this right here, fast, which means it's going to weigh small amounts. But charge also affects the way it is, because if something is doubly ionized, I mean, that's a whole new thing, right? Very advanced topic, but it's true. But speed. So just in a minute we can figure out how much something weighs, which brings me to problem number 37, hydroquinone.